let's talk about what can go wrong and when values do not follow normal distribution or when we are not allowed to use normal distribution. Okay. So remember, what is normal distribution? So normal distribution is this distribution of values, of density of the values that looks like a bell-shaped curve and is described by a Gaussian function that we discussed so far. And when can we use normal distribution? Well, apparently when empirical data, for example, if you have a lot of values and if you make a distribution histogram, empirical distribution histogram, distribution of frequencies, densities of frequencies, it matches the theoretical distribution well, like it's shown on this plot. But on the other hand, you remember that for a small sample size, we cannot trust histograms because you simply don't have enough values to accumulate for making a good histogram. So what can we do in this case? Well, let's talk about this. Well, first of all, let me show you some populations which do not follow normal distribution. And then you can see very common kind of deviations from normality here. In this case, you can see I write it like right skew. The distribution is skewed, so it's not symmetric. And you can see this is a theoretical distribution. Here we have the most expected value. But for the empirical distribution, the most expected value is located here. Why so? Because we have, you can see that if you think about tail, so this is the center of your distribution, the most expected value, this tail and this tail, they have the different size. So you have some extreme values on the right side. That's why it's called right skew. Okay. So when it happens, most of the time you have skewed distribution if your values are bounded. For example, you have a value which cannot go beyond 0 and 100. You measure percent of correct answers. In this case, most of the time you will have a skewed distribution. So this is the left skew. By the way, imagine that this is 100, this is 0%. So that's what I would like to see in my courses, right? And most of the students, they have high scores, and then very few have some low scores as well. Okay, so this is the left skewed distribution. What else you can see? You can also see some outliers on both tails. In this case, we talk about this distribution has a wrong kurtosis, so it's too peaky. Or you can also have bimodality or bimodality. What it means? It means that you have more than one peak. So you can see it's kind of two distributions. So this is one distribution, this is the second distribution. So the bar with the highest frequency, we call it mode. We will also talk about this in the last block, number 4. And then you have another mode here. So it's two modes. So it's two kind of peaks of your distribution. That's called bimodal distribution. Most of the time you see bimodality or trimodality or so on and so forth if you have several populations. For example, if you think about height of adult males and females for the same ethnicity, very often, because we're biologically a little bit different, very often you will see this bimodality in the height distribution. Or you can think about, for example, distribution of salaries from the different regions, for example, from the north of Europe and from the south of Europe. Apparently, they also will have different expected values, right? Okay, so if populations are not normally distributed, how you can check it, how you can find this, and how you can understand that you are not allowed to use normal distribution to describe the sample because it came from not normally distributed population. Well, the first simplest statistic that you can compute for your sample, it's called skewness. Skewness is exactly the measure of symmetry. And we already discussed what is a left skew, what is a right skew. Here you can also see the consequences of the skewed distribution. You can see here I have mode. You remember mode, it's the bar with the highest value. And then this is the median and this is the mean. In theoretical normal distribution, mean and median are the same because theoretical normal distribution is completely symmetric. So mean and median are the same. But if you have a skewed distribution, like in this case, you remember that median is kind of stable to outliers. So if you have outliers on this tail, they will pull the average towards these outliers. But the median will be more stable to outliers. So we'll have a discrepancy between mean and median. So you will have a difference between mean and median values. So mean will be closer to in this case, to the right tail, right? If you have a left skew, you will have the same effect. So in this case, mean, you have extreme values here. They kind of pull the mean towards these extreme values. But median, you remember, it's stable to outliers, so therefore it remains unchanged. So therefore, you will have also this difference. So in this case, mean will be smaller than the median. Okay. Then what you can do, you can compute the skewness. Skewness is a measure of the symmetry. For absolute symmetric distribution, regardless normal or not, just symmetric, the skewness is 0 because you can see how it's computed. You take a z-score of your sample, and then you take them in the power of 3, right? So why 3? Because you remember, z-score can be negative, can be positive. In this case, sign matters. You need to kind of see, is there a balance between negative and positive values? And so you kind of, by taking a power of 3, you multiply the magnitude of the z-score, right? So if it's a -2 in the power of 3, it will be -8. If it's +2 in the power of 3, it will be 8. And then you simply take a sum of these z-scores, and then you do some transformation based on the sample size, and that's what is called skewness. So apparently, if your z-scores are symmetric, you have equal amount of negative and positive values, and the magnitude of negative and positive values is more or less the same, then the sum will be close to 0, and therefore the total skewness will be also close to 0. But if you have more negative values, or maybe no more, but these negative values have larger magnitude, then the z-score, the skewness will be also negative. If you have other way around, you have a lot of positive values, positive z-scores, I mean, or you have not more positive z-scores, but these positive z-scores have larger magnitude, then of course you will have a positive skewness. Okay. So this is just an illustration, very simple. So if you have a right skew like this, like blue curve, then your values, the skewness will be positive. If you have left skew, the values will be negative. Okay. Let's calculate the skewness. We already have z-scores, right? So first of all, you need to compute the third power. So you take every z-score in a power of 3. So this is the power of 3. Then you take a sum. And then you can see the sum is actually relatively small, right? It's not 0. So we have a positive skewness, but it's a relatively small number. And then if you normalize it using the sample size, then you can see this is the skewness. You got 0.25. It's not 0. It's a little bit positive, but it's a sample size of 10. So everything is possible in this case. So therefore, in this case, this 0.25, I would assume that it's a good skewness. So it looks like our distribution is at least symmetric. Okay.